All right, so all well and good. Now, if we go back to let's run this program again. We said that these wavefronts change direction, right? The direction of propagation actually changes. The light rays bend inside the material. So these red lines are the light rays. They change direction. And this is a phenomena called, in fact, refraction. Okay, so the index of refraction has to do with this phenomenon. And so what we want to do is see how much, or at least see if we can quantify how much the light rays are bending when we go from one material to another. So I'm going to go through a little derivation here, doing some geometry mostly. This is in the book. It can get a little hairy kind of drawing all this out. So if you just want to kind of see how it's done, not worry too much about copying it all down because it is in the textbook. But I'll just show you where this comes from. Here's the interface between the two materials. Okay, so here's the interface. And this is, call it medium number 1 and medium number 2 on this side. And what I'm going to do is basically zoom in on one point or one part of this diagram here and show these wavefronts coming in right at the surface. And let me draw these in different colors here. So here is, in the first medium, we have a wavefront, and then another wavefront, and this perpendicular distance between the two wavefronts is the wavelength. So this is lambda 1. Okay? We'll call this angle theta 1 between the surface and the wavefront. Okay? Now we see that those wavefronts bend a little bit, so I'm going to draw those in the new material. Here is a wavefront. Here's another wavefront. And say another one up here maybe. We can draw this. So I'm try to draw a wavefront way up here, about the same distance away, and another wavefront here. And this perpendicular distance is the wavelength in the second medium. So I'll call that lambda 2. Okay. So the way to think about this is this wavefront is traveling this way, and it bends inside here, and this wavefront is traveling this way now. And they share, if we look at these two triangles. So here's a right triangle, and here's another right triangle. And let me call this angle theta sub 2. And this side that's shared between them is D. Okay. We do a little trigonometry. We say, okay, look at this this right triangle. We have the opposite side over the hypotenuse is going to give me the sine of the angle. So I can say that sine of theta 2 is lambda 2 over D. But sine of theta 1 is the same thing. Sine of theta 1 is lambda 1 over D. And D is the same. That hypotenuse is the same for those two triangles. So I can do a little rearranging here and come up with that D has to be equal to lambda 2 over sine theta 2, and that's got to be equal to lambda 1 over sine of theta 1. So those two things are the same. We also say that, again, the wavelength is going to be equal to the speed, v1, times the period, or speed divided by the frequency. And the period and the frequency are the same for both materials. So I can say that we have v1 t over sine theta 1 is v2 t over sine of theta 2. and the t's cancel out. And then by definition, we said that this index of refraction is c over v, so n1's index of refraction is c over v1, and n2's index of refraction is c over v2. And if I plug that in, by just saying v1 is c over n1, plug that in, I'm going to get c over n1 sine theta 1 is equal to c over n2 sine theta 2, and the c's will cancel out. And so we're left with this relationship. N1 sine theta 1 is equal to N2 sine theta 2. If I do a little geometry, now I measured these angles from the interface. If I do a little geometry, I can show, I'm going to draw a line that is perpendicular to the interface between the two materials, okay? You can show that this angle between this light ray, because again, the line perpendicular to the wavefronts is a ray, so that's a ray. And here's another light ray. That's the ray in the second medium. If I draw a line from the perpendicular to the ray, I'll call that the angle, the incident angle. And that's theta the same as theta 1, and this is the same as theta 2. So we can quantify how much, if I know the index of refraction for the two materials, and I know how much the light ray bends in one medium, I can find out how much the light ray is going to bend in the second medium. This is called Snell's law. And it's just the basic law behind this field of geometric optics. It says, it's telling us how much the light ray bends, the light ray bends from the normal. And that normal is a line that's perpendicular to the surface, perpendicular to the interface between the two materials. So let's try a simple example, and then we'll have you guys do one. Something really simple. Let's say you have just a tank of water here. Okay, so I'm going to draw the surface of the water. So here's water, and here's air. And I have a laser beam, maybe like a laser pointer, and I'm going to shoot this, shine this laser pointer in this direction, and I draw the normal to the surface, and that laser beam is going to bend when it goes through the water. Okay, so I'll call again that theta 1, the angle between the normal and the light ray, and this is theta 2. Okay, let's say theta 1 is equal to, I don't know, 30 degrees. We know N1 is equal to 1.0029. The index of, so I'm calling this 1 and this 2, basically. N2 is the index of refraction of water, so that's 1.33. So go ahead and try it. See if you can use Snell's law, N1 sine theta 1 equal to N2 sine theta 2. See if you can solve for theta 2. Solve for the the angle that the laser beam makes in the water. What'd you get? 22 degrees? Theta 2 is 22 degrees? Okay. So it just comes from solving for sine of theta 2 is N1 sine theta 1 over N2, and then you just take the arc sine or the inverse sine of that result, right? And you should have 22 degrees, okay? So we see that this angle was 30 degrees, and it becomes smaller when it goes into the water, okay? Well, we could have, so we went from, so let's just recap. We went from a low index of refraction, air is only 1.0029, to a higher index of refraction, and we saw that the light ray gets bent toward the normal. And you could show that's a general result. What about this? Let's say we have a beam of light traveling upward through glass into water. Now you might say, well, how in the world can that happen? Well, I don't know. Maybe you have a glass, okay, some glass container, and you have a light down here, and you're shining light up into the glass, and then it goes into the water that it's containing. Or maybe like a light at the bottom of a pool, okay? If you have a light that's enclosed in a glass fixture, and it's shining upward into a pool of water, it starts down here, and it's going up here. Now, the subscripts, you got to be a little bit careful here. Theta 2 is referring to the index or the angle in glass. Theta 1 is the angle in water. And theta 1 is the thing we're trying to find. Okay, so it makes an angle of 20 degrees with the normal while in the glass. At what angle does it emerge when it goes into the water? And again, the diagram's not to scale. Indices are 1.33 for water, 1.46 for glass. Let's try it out, see what we get. Oh, say that one more time. If it's perpendicular, so if it goes through, you're talking about like you have a surface here, and the light ray goes straight down, then it's not going to refract, right? Because theta 1 is equal to 0, and theta 2 is equal to 0. Yeah, that's right. And you kind of saw that in the demo, because you saw that as those light rays moved farther away from, that one was sort of straight on, right? That one bent kind of like that, and the farther away you moved, the more bending there was from the normal, right? Okay, so the question is, what happens if the light ray stays the same direction, but the interface changes? Well, if your surface changes angle, then your normal is going to change angle too. So that's going to affect. Yeah, well, it's going to depend. It's going to vary back and forth. But the key idea here is not the direction of the light ray, but the direction with respect to that normal. And if that normal changes, then the refraction angle is going to change as well. Oh, well, it depends on the. Okay, so it depends on the source. Okay, now let's say you have a source of light that's emitting light in all directions. Okay. Well, it could emit, even way out here, right? And I could go arbitrarily far away, and Snell's law is still going to apply. If I have an angle that's very big, I have that's theta 1, and then theta 2 is going to be something like that, and I can calculate what theta 2 is. Now you have a limit where it's getting so far away that the angle is 0, right? But as long as there's a non 90 degree theta 1 here, and we're going from air into water, there's going to be some refraction, and we could calculate that. Now, if we're going the opposite direction, that's a different story. We'll get to that in just a second, okay? But what do we got here? We get, answer number 5, 22.1 degrees, which is just a pure coincidence. It's the same numbers we got last time. It's not every refraction is 22 degrees. But okay, we get the same. We go through the same type of reasoning. We find that in this case, what happened? We went from an index of refraction that was large to an index of refraction that was smaller. And what happened to the light ray? The angle got bigger, right? So the light ray got bent away from the normal, right? Got bent away from the normal. So here's a case where we have a light ray. So we went from a lower index to higher. Light ray is bent toward the normal, toward that perpendicular line. In the other case, we had a light ray going from a higher, and again, this is an exaggerated picture, but we have a higher N and a lower N here. If you go from a higher to a lower end, you have light ray bent away from the normal. This is going to be true all the time. You got to be a little bit careful when you're making generalities here, though. When you're going from a higher to a lower index, because something strange can happen. Here's a question. Let's see if we can try this out. A beam of light in water makes an angle of 65 degrees to the normal. So again, we have light coming out of the pool and going up into the air. So you have like a flash or a flashlight or a light down at the bottom of a pool. Beam of light in water makes an angle of 65 degrees to the normal. When the beam emerges into air, what angle does it make with the normal? Okay, none of the above, because what happened? What did you get with your calculator? Error message, right? What happens? You have a sine of an angle that's bigger than 1, right? We've got a problem. We say n1 sine theta 1 is n2 sine theta 2. And so you have theta 2 being equal to the inverse sine of n1 over n2 sine theta 1. And so that's the inverse sine of 1.33 divided by air, which is 1.0029. So it's essentially 1.33. It's approximately 1.33 times the sine of 65. And that number inside the parentheses turns out to be 1.205. You can't take the sine of an angle, the inverse sine of a number bigger than 1. So we go, what's going on here? Well, it turns out that this angle is bigger than what's called the critical angle. At some point, we reach a point where refraction, let's look at it this way. If I'm going from a lower to a higher index, again, that light ray gets bent away from the normal. But I could imagine increasing this angle until the light ray is somehow bent at 90 degrees from the normal. So here is, say, the water, and here's the air. And here is some theta 1, which is going to be, I'm going to call the critical angle. And theta 2, we're going to say, is 90 degrees. So you can calculate that critical angle. We know we have n1 equal to 1.33 and n2 approximately equal to 1. It's 1.0029, but let's just say it's 1. Use Snell's law and see if you can find what theta 1 is equal to. That's right. So at a certain, beyond this angle, we basically reached the maximum amount of refraction, right? Anything beyond this is going to produce a sine of an angle, or a sine inverse sine in here greater than 1, right? And so you just can't see that. That light's just not going to escape. And that's called total internal reflection. Okay? So anything beyond this, there is no refraction, and what we're going to see is just pure reflection inside the material. So this is called total internal reflection. Anybody get the angle? What is it? 48 point what? 48.9? So about 49 degrees, okay? So what this is saying is that for at least for the water-air interface, it may be different depending on the materials, but for the water-air interface, if you have a light going from the water to the air, and it's at an angle bigger than this 49 degrees, in the previous problem the angle was 65, so it was definitely bigger than 49 degrees, you're going to have what's called total internal reflection. No light is actually going to escape, and it'll just be purely reflected inside the material. So let's see if we can try it. Here is a tank of water. And make sure everybody can see this here. Let me see if I can move it without spilling it. So I have here just a lamp that I can change the angle with, and here is the along the 90-degree line, or along line here, we have just a surface of water with air, and I'm going to turn the light on. And so when it's at a zero angle with the normal, the light just goes straight up, right? And as I increase the angle, we see the angle increasing with the normal in the air as well, until I reach somewhere around 45, 46, 47, 50 degrees. And right around 50 degrees, you can see, can everybody see that? You can see total internal reflection, right? There's no light actually escaping. Now, there's some combination of the two when you're kind of at that critical point, until you go past that critical angle and it completely turns into total internal reflection. Okay? So the key point here is that when you're going from lower to higher index, the light ray is always bent toward the normal. When you're going from higher to lower index, the light's bent away from the normal, but you got to be careful and worry about that critical angle. If you're beyond that critical angle, you're going to have total internal reflection. Okay? We will deal more with this on Wednesday.